Yeah, I can imagine. Out here it's not too bad. I'm actually pointed to the southwest, which is pretty surprising because it looks like you're kind of closer to the northeast of me. And I've been picking up a lot more towards the southwest of the broadside for my inverted V, over.
Antennas are one of the most important parts of any amateur radio station, even though many beginners tend to focus first on radios, microphones, and power levels. The antenna is the device that actually connects your radio to the air, allowing your signal to leave the transmitter and letting distant signals return to your receiver. In many cases, a well-designed antenna can make a much bigger difference in real-world performance than a more powerful radio. An antenna serves as the interface between the electrical signals inside your equipment and the electromagnetic waves that travel through space. It lets your radio talk to and listen from the air around you. When you transmit, your radio sends radio frequency current into the antenna, which then creates an electromagnetic field and radiates energy outward as radio waves. When you receive, passing radio waves induce a small alternating current into the antenna, which is then carried into the receiver and converted back into sound or data. In this video, I will discuss basic concepts related to the design and function of 4 different antennas popular with amateur radio operators. Before I jump into specific antennas, let me talk about one of the most important concepts for new operators to understand. I am talking about resonance, and we'll describe it this way. An antenna works most efficiently when its length matches the wavelength, or a specific fraction of the wavelength, of the frequency being used. When the antenna is resonant, it transfers energy more effectively, radiates more of your signal, and reduces wasted power and heat. At resonance, the impedance of the antenna is largely resistive and often near 50 ohms, which matches most amateur radios and feed lines, resulting in less reflected power and a lower SWR. If an antenna is too long or too short for the operating frequency, it becomes mismatched and less efficient, meaning that less of your transmitted signal reaches the air. When resonance cannot be achieved physically, an antenna tuner can help the radio and antenna system electrically match so the transmitter operates safely and efficiently, even though the antenna itself has not physically changed. A few other key ideas help beginners better understand how antennas behave. Polarization refers to the orientation of the antenna, whether it is vertical, horizontal, or circular, and signals are generally stronger when both stations use the same polarization. Gain and directionality describe how antennas distribute energy in space. Some antennas radiate fairly evenly in many directions, while others concentrate energy into a preferred direction. Structures and nearby vegetation can significantly affect how an antenna performs. Buildings, metal roofs, wiring, HVAC ducts, stucco mesh, foil-backed insulation, and other conductive materials can absorb or reflect RF energy, which can distort the radiation pattern, increase losses, and detune an otherwise well-built antenna. Trees and vegetation, especially when wet, can also absorb RF energy, most noticeably on VHF and UHF, where wavelengths are shorter. In some situations, an antenna can be installed in an attic or inside a house and still work, especially on HF bands where signals can tolerate more environmental loss, but efficiency will usually be lower and noise levels may be higher. If an attic installation is necessary, it helps to keep the antenna as far as possible from wiring, ducting, and metal structures, and to retune or trim the antenna after installation because the surrounding materials can shift its resonant frequency. Whenever possible, placing the antenna outdoors, higher above ground, and in clearer space, even a few feet away from the structure or mounted on a small mast or tree, will generally improve performance, reduce losses, and provide a cleaner radiation pattern, will transfer more power and reduce signal reflections. A radiation pattern describes how an antenna sends or receives radio energy in different directions. Instead of thinking of an antenna as pushing a signal out evenly like a light bulb, a radiation pattern shows that energy is distributed unevenly, strong in some directions and weaker or even absent in others. These patterns are typically visualized as 2D or 3D shapes, where the bulges, called lobes, represent strong signal areas. Antenna nulls are directions in which an antenna radiates very little, or sometimes almost no, signal energy. These nulls are a natural result of how radio waves combine and cancel each other in space based on the antenna's shape, orientation, and design. For example, a simple dipole antenna has strong radiation broadside to the wire, but off the ends of the antenna, the signal drops off sharply. Those directions are its nulls. This happens because the electromagnetic waves coming from different parts of the antenna arrive out of phase in those directions and effectively cancel each other out. While nulls might sound like a disadvantage, they can actually be useful. Operators can take advantage of nulls to reduce interference or noise coming from a specific direction by orienting the antenna so the unwanted signal falls into the null. Understanding where an antenna's nulls exist helps operators position and aim their antennas more effectively, improving communication quality and control over where signals are transmitted and received. As you probably have already guessed, the 4 antennas that I am talking about are the loop antenna, the vertical antenna, the dipole antenna, and the Yagi antenna. I'm not going to take them in that order. I am going to start with the easiest to build. The center-fed and vertical antennas are in competition for the top spot. A center-fed wire dipole is one of the simplest and most effective antennas you can use. It's made of 2 equal-length wire elements, with a coaxial feed line connected right at the center. This point is called the feed point, where the radio signal is applied. Each side of the dipole is typically cut to about 1/4 wavelength, so together they form a half wavelength antenna. When energized, the antenna radiates most strongly broadside to the wire, that is, outward from the sides of the dipole, while very little energy is radiated off the ends. This creates a characteristic figure-8 radiation pattern. Because the antenna is balanced, current flows evenly in both directions from the center, contributing to its efficiency and predictable performance. The key takeaway is that center-fed dipoles are simple, efficient, and easy to build, making them a go-to choice for many operators. For best results, they should be mounted in the clear and as high as practical to improve radiation and overall signal reach. A vertical antenna is a simple and highly effective design that uses a vertical radiating element mounted over a ground plane to transmit and receive signals. The signal is fed at the base through a coaxial cable connection called the feed point, where energy from the radio enters the antenna. From there, the vertical radiator sends energy outward evenly in all horizontal directions, creating an omnidirectional radiation pattern that provides full 360-degree coverage, ideal for communicating in any direction without repositioning the antenna. Beneath the antenna, the ground plane, made up of radio elements, acts as a reference surface and is essential for efficient operation, helping the antenna radiate properly. The height of the vertical element also plays a key role in performance, influencing how effectively signals are transmitted and received. The key takeaway is that vertical antennas are simple, reliable, and excellent for both local and long-distance, or DX, communication, especially when installed at a good height with a solid ground system. A Yagi antenna is a directional antenna designed to focus radio energy in one specific direction, making it ideal for longer-range communication. At the center of the antenna is the driven element, which is the only part directly connected to the feed line and actively radiates the signal. Behind it sits the reflector, a slightly longer element that bounces energy forward, helping reduce signal loss to the rear. In front of the driven element are several directors, which are slightly shorter elements that guide and concentrate the signal even further in the forward direction. Together, these elements work as a system to create gain, meaning a stronger, more focused signal, while minimizing radiation in unwanted directions. The result is a clear direction of maximum radiation, shown by the forward arrow, where signal strength is strongest. The key takeaway is that Yagi antennas excel at focusing energy for improved range and performance, and to get the best results, the antenna should always be aimed so the directors point toward the target signal. A loop antenna is a compact and versatile design made from a closed loop of wire, and it operates by responding primarily to the magnetic component of radio waves. This unique characteristic makes it less sensitive to electrical noise, which is why loop antennas are often valued for cleaner reception. As shown in the diagram, the antenna is most sensitive to signals arriving broadside to the plane of the loop, meaning signals coming from the sides produce the strongest response, identified as the directions of maximum signal. In contrast, signals that pass straight through the center of the loop, along the edge view, are greatly reduced, creating what is known as a null. This null is extremely useful for rejecting unwanted signals or interference. The feed point, located at the base of the loop, is where the coaxial cable connects through a matching network to properly transfer the signal to and from the radio. The key takeaway is that loop antennas provide directional reception with a very pronounced null, allowing operators to rotate the antenna to maximize the desired signal while minimizing noise and interference. Because I made a comment about a matching network when talking about the loop antenna, I feel I need to explain what the term means. A matching network in amateur radio is a circuit that ensures your transmitter, feed line, and antenna all work together efficiently by matching their impedances, typically to 50 ohms. When your radio sends RF energy down the coax, it expects to see that specific load, and if the antenna system doesn't match, some of the signal is reflected back instead of being radiated, leading to high SWR, reduced performance, and possible stress on the radio. A matching network acts like an electrical adapter, transforming the antenna's impedance, whether it's higher, lower, or complex, so the radio sees the proper load and can transfer power effectively. This can be done using devices like antenna tuners, baluns, ununs, or internal LC circuits made of inductors and capacitors. In systems like loop antennas, where the natural impedance isn't 50 ohms, the matching network is essential for proper operation, helping deliver power efficiently while preserving the antenna's performance. The key idea is that a matching network doesn't create more power or improve a poor antenna setup. It simply allows the system to operate as efficiently as possible. Before I make my final comments, I want to introduce you to the antenna our instructors always recommend as a first antenna build. The quarter-wave ground plane antenna is the first antenna beginners should build because it strikes a near-perfect balance between simplicity, performance, and learning value. First, it's easy to construct. The design uses just a few basic parts: one vertical radiator and typically 4 ground radials, all cut to roughly a quarter wavelength. There's no complex matching network required in most cases, and it can be built with simple hand tools and inexpensive materials. Second, it's electrically forgiving. A properly built quarter-wave ground plane naturally presents an impedance close to 50 ohms when the radials are angled downward, around 45 degrees, which means it matches well with standard coax and most radios without needing a tuner. That makes it ideal for beginners who are still learning about SWR and impedance. Third, it delivers solid, reliable performance. It provides an omnidirectional radiation pattern, meaning it transmits and receives equally well in all horizontal directions. This makes it excellent for general communication, local contacts, and repeaters without needing to aim the antenna. Fourth, it teaches core antenna concepts. By building and using one, beginners learn about wavelength and element length, ground planes and radials, feed points and coax connections, radiation patterns and antenna height. Finally, it's easy to experiment with. Beginners can adjust radial angles, change element lengths, raise or lower the antenna, and immediately see how those changes affect performance. That hands-on feedback is incredibly valuable for learning. In short, the quarter-wave ground plane is the perfect first success antenna. It works well, builds confidence, and lays the foundation for understanding more advanced antenna systems. My final message for beginners is this. The most important lesson you can learn is understanding that a modest radio paired with a good antenna will almost always outperform a powerful radio feeding a poor antenna system. Height, placement, grounding, surrounding structures, and installation quality all play major roles in how an antenna performs. Amateur radio is an experimental and learning-oriented hobby, and every antenna, even imperfect ones, helps build knowledge and experience. Start simple. Experiment with basic designs like dipoles and verticals, try loops when space is limited, and grow your station as your understanding increases. In many ways, the antenna is not just another piece of equipment, it is your true voice on the air.